On this review. So we're just basically taking the derivative of everything. So the first one is just the derivative of secant. Remember, the derivative of secant is secant tangent. This does involve the chain rule. So our argument, which would be this guy, that doesn't change. So when you take the derivative of secant, all right, here's a bunch of derivatives. So the first one, we're taking the derivative of secant, and the derivative of secant is secant tangent. And when we take the derivative, the inside doesn't change. The argument of the trig function remains the same. And then this 12x squared is just the chain rule, right? We have to take the derivative of the argument. The derivative of 4x cubed plus 3 then is 12x squared. Second one, we have multiple pieces here. The first piece is power rule. It's this thing to the 10th. And so bring the 10 down, decrease the power by 1. The inside stays the same. Then we have to multiply by the derivative of the inside. Now, this is cosine of x cubed, which is much different than cosine 3x. That's cosine x cubed. So just be careful of where that 3 is located. That 3 is actually cubing the x, not the trig function. So the derivative of negative cosine is sine. Argument stays the same, and then times the derivative of the inside, right? The derivative of 7 goes away because the derivative of a constant is 0, and so we end up with those 3 terms. This next one, I wouldn't be too concerned tomorrow. Tomorrow or whenever we take this test, this is acceptable tomorrow. You can just stop there. This is where you would need to be able to get to if it was an AP test, because an AP test will be a multiple choice question, and they will likely simplify on an AP test to the most simplified algebraic version. But for tomorrow, we can do this, and all I'm doing is product rule. I take the first function, 6x minus 1 to the 4th, times this, which is just some power rule with chain rule, plus the second function times the derivative of that first guy. So it's just power rule and product rule. This right here is totally acceptable tomorrow. Same thing over here. Tomorrow you can do it either way. You can bump that up and do product rule and treat this as 8x times 5x minus 2 to the negative 1/2 power, or you can do quotient rule. It looks like I did quotient rule. Quotient rule would be the bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom, bring the half down, decrease it by 1 to make it a negative 1/2. Thus, it's in the denominator times the derivative of the inside, which is that 5. All over the denominator squared, right? V u prime minus u v prime over v squared. And what I did, it looks like I added subtracted fractions, and I get down to this thing, right? Again, you will not have to do that tomorrow on the test. However, if this was an AP question, this would be the final answer. All right, 5 and 6 look like both implicit differentiation. You've got to be able to take derivatives with respect to y being a function. And so this is just easy. If x to the 4th is just 4x cubed, and then minus, and then I did product rule. Or no, I didn't do product rule. I did do product rule, but I did the rule is the derivative of tangent. The derivative of tangent is secant squared. So it's the secant squared of xy times the derivative of the inside. The derivative of xy is a product rule. So first function x times the derivative of the second, y prime, plus second function y times the derivative of x, which is just 1. Okay? Then I distributed the secant squared, boom, boom, and got 2 terms with secant. And then it looks like this guy and this guy don't have y prime. So they're going to chill, and I'm going to add that secant squared term to the other side. Then I'm going to factor a y prime, and then that will leave a 4y to the 4th plus secant squared xy x. And I'm going to divide by that and then get that answer. This is what you have to be able to get here tomorrow, right? In implicit differentiation, you've got to be able to get to what's y prime equals. Now, there can be y's over here. That's fine. But you do need to get y prime equals something. Same thing here. Power rule, product rule, power rule. Be careful on the power rule for y, because you are going to multiply by y prime, right? Y is a function of x. Same thing. Everything that doesn't have a y prime, it looks like I moved to the right side of the equation. Everything that did have a y prime, it stayed, and then I factored a y prime, and then you're going to divide by that common factor at this point and move it over. Same thing here. I'm not going to ask you for tangent and normal lines tomorrow. Tomorrow is all about just taking derivatives, so you just got to be able to get to this point. However, tangent and normal lines will be on the multiple choice version. And remember, the derivative is the equation for the slope, so you're just putting in 2 for x, 1 for y, and finding the slope at that point. And then you have the point 2 comma 1 in a slope. Remember, the normal line is the opposite reciprocal slope. It's also perpendicular. It's also called orthogonal. All those words mean the same thing. And so since the tangent line is a slope of 1/5, our normal line is going to have a slope of -5. Logarithmic differentiation is a useful technique. So instead of doing some crazy product power quotient rule over here, I can apply logarithms to both sides. I can use logarithms to say like the logarithm of a, b over c is really the logarithm of a plus the logarithm of b minus the logarithm of c. And then I can use the power property of a logarithm to bring those down, bring the half down, bring the 5 down, and then I got a nice easy derivatives of logarithms. Remember, the derivative of the natural log of u is 1 over u times u prime, so that the derivative of the natural log of y is 1 over y times y prime, which is the same thing as saying y prime over y. And then I multiply by y, and since I know what y is, I can take that value and plug it back in for y and get this big thing. Again, this is what you would have to do tomorrow on the test. Okay, I don't know why I say that. Maybe just because there was enough people that forgot how to take the derivative of a to the u. Remember, the derivative of a to the u is a to the u times the natural log of a times u prime, where the derivative of e to the u is e to the u times u prime. You skip this natural log of a, but really, the natural log of e is 1, so those rules are actually identical, right? A is just some number. So this one is power rule, this is exponential, and this is really just x to the 5/4. So just rearrange that a little bit. The derivative of 3 pieces is really just the sum of those pieces. 10, well, we got exponential and a power rule, which is really just product. And then I did factor that out. Again, this tomorrow is totally fine. You can leave it as that. On the AP test, get it to there. 11. So we have a negative exponential, which is fine, right? The derivative of e to the u is just e to the u times u prime. So you're just going to get a -20 when you take a derivative, because you're going to get a -5 and then a 4. And then the derivative of the natural log is 1 over u times u prime. And it does turn out that that thing simplifies to that. 12 is a logarithm. Again, this is just the rule. The derivative of log base b of u is 1 over u times u prime divided by the natural log of b. So you just create this extra factor of the natural log of 6 when this is a 6 rather than a natural logarithm, which is base e. Inverse tangent, there's your rule. The derivative of inverse tangent is 1 over 1 plus u squared times u prime, which is the same thing as just saying u prime all over that. The derivative of inverse cosine is stupid, and it's like minus 1 over 1 minus u squared times u prime. Again, I'm not going to make you do that on the test tomorrow. I indicated in class the only important inverse trig function is inverse tangent. You have to know everything else, but you don't need to know the other inverse trig rules. You got to know all the trig rules, just not the inverse trig rules except for inverse tangent. Okay, this is not an exponential, and this is not power rule. This is a different type of function, and the only way we can deal with it is that we can actually apply logarithms to both sides and manipulate it algebraically, right? Algebra before calculus. So apply logarithms to both sides. Use the property, power property of a logarithm and bring that 7 down, and what we've done is we've turned that crazy function into product rule. So the right side is product rule, the left side is implicit, right? The derivative of the natural log of u is 1 over u times u prime. So the natural log of y, if we take its derivative, we get 1 over y times y prime. Y is equal to this, so then we move the y over here, we can substitute it back in and get this as our final answer. Again, tomorrow, that is the only acceptable answer. And then 16, I guess that's the last one. It's all about this chain rule tables. just remember this is like the definition of the chain rule and just being careful. So it looks like I take the derivative of g, and so I get g prime of f of x minus 2 times the derivative of the inside, which is just f prime, and then I plug in 2. So I'm doing like f prime of 2, f of 2 minus 2, f of 2 is 5, 5 minus 2 is 3, so then I need to do g prime of 3 times f prime of 2, and you can find those values in the chart. Down here, this is like a little chain rule and a little like product rule. So this is f cubed times g squared, so then f cubed times the derivative of g squared, which is 2g prime, plus g squared times the derivative of f cubed, which is 3f squared f prime. And then you just got to be careful and plug all those values in. You get some ridiculously big number using the tables. Okay, I did say that the chain rule table questions will likely be on the multiple choice, where tomorrow you have 16 questions. They're all derivatives, and you just, they all look just like this. Take that derivative, take that derivative, take that derivative, take that derivative. You don't have to simplify, other than like on implicit, you do have to solve for y prime, and if you apply logarithms to both sides, like on, where was that one? Like on this one, then you do have to actually put back in y, because you introduce the logarithms and then go ahead and reverse. So this review is a very good example of the length and difficulty of the test tomorrow, but certainly you should review all your derivative rules and be comfortable with all those situations.